This video will look at the definition of an exponential function, its properties, and go through 3 examples where we use a property to solve an exponential function. So remember that when we take a to the r, where r is a rational number, r is a fraction, then we turn that into a root. So a to the m over n power is the nth root of a raised to the m power. For example, 16 to the 3/4 power is equal to the 4th root of 16 cubed. Now the 4th root of 16 is 2, and 2 cubed is 8. Here's a couple of examples where the exponent is negative. So remember, negative exponents tell you to take the reciprocal. So 27 to the negative 1/3 is equal to 1 over 27 to the positive 1/3. The 1/3 power translates to the cubed root. So now we have 1 over the cubed root of 27, which is 1 over 3. In a similar way, 64 to the negative 1/2 is equal to 1 over 64 to the 1/2 power. The 1/2 power translates to the square root of 64, so we have 1 over 8. So in this section, we're going to look at perhaps things like 2 to the square root of 3. What do you do when your exponents aren't rational numbers? They're not just fractions or something else. Now, it turns out that the same rules that we've been using on exponents apply whether we have rational exponents or whether we have irrational exponents. And if we have an equation such as y equals 2 to the x power, then as long as x is a real value, we get exactly one value of y, which is the definition of a function. And this is some examples of some properties. So if I have a base of 2, then 2 to the x equals 2 to the 4th tells me that x equals 4. If my bases are the same, the exponents have to be equal. And vice versa. If x equals 4, then 2 to the x equals 2 to the 4th. And there's nothing special about the base 2. I could use any base. 15 to the x will equal 15 to the 4th. There's some relationships regarding larger and smaller. 4 squared is less than 4 cubed. The bases are the same, and 2 is less than 4. However, 1/2 to the 2nd power is greater than 1/2 to the 3rd power. And the reason that is because it matters about our base a. If our base a is bigger than 1, so 4 is bigger than 1, then the relative size of the exponents tells us 4 squared is less than 4 cubed. But if our base is in between 0 and 1, then it's the opposite. And here are these properties written out generically. It's really important that our base be greater than 0. So a has to be greater than 0, and a cannot equal 1. The reason that a can't equal 1 is because if it does, then we don't get property a. A to the x power would not be unique if a was 1. So as long as a is not 1 and a is 0, these 4 properties apply. The most important property is the one in red. That's the one we're going to use to solve some equations in a few examples. A to the b equals a to the c if and only if b equals c. In other words, if the bases are the same, the exponents are equal, and vice versa. Here's an explanation of why a has to be greater than 0 and a cannot equal 1. We can treat these like any other function. So f of negative 1 means replace the x with negative 1 and solve. So 2 to the negative 1 equals 1/2. F of 3 means find 2 to the 3rd power. That equals 8. F of 5/2 means find 2 to the 5/2 power, which we can split up into 2 parts exponent-wise. 2 to the 5th to the 1/2 power. 2 to the 5th is 32. The 1/2 power means square root. We want to simplify the square root of 32. 16 times 2 gives us 32. The square root of 16 is 4, so we end up with 4 square root of 2. F of 4.92, we have to use a calculator and do a little rounding. Now the definition of an exponential function again requires our base, a, to be greater than 0 and not equal to 1. So f of x equals a to the x power defines an exponential function with a base of a. Essentially, an exponential function has an exponent that's a variable. So x is the variable here, and a is not. Just another reminder about not allowing 1 as the base of an exponential function. We don't get a unique value, as we saw on that first property on that list of properties, if a is 1. If you're interested in the graph, here's a graph of an exponential function where our base is greater than 1. The table is a picture of 2 to the x power. The graph is just a generic a to the x power. Here's a picture of a graph where a is between 0 and 1, so it's a fraction. The table is for the particular graph of 1/2 to the x power. The graph is just generic a to the x, where a is a fraction between 0 and 1. Now, how do we go about solving these exponential equations? It all comes down to that property b. A to the b power equals a to the c power if and only if b equals c. In other words, if the bases are the same, the exponents have to be equal. So we need to figure out, how do I write these bases to be the same? The strategy is to find the smallest value and rewrite each base using that smallest value. And what I mean by that is we have the numbers 1, 3, and 81. Notice I am considering the numerator separate from the denominator. Now we've already seen we can't use 1 as the base, so we really are only considering the numbers 3 and 81. 3 is the smaller value. Is it possible to write 1/3 as 3 to a power? Is it possible to write 81 as 3 to a power? The answer is yes in both cases. 1/3 is the same as 3 to the negative 1 power. The rules of exponents now tell me I can take the negative 1 and multiply it by the x, and now I have 3 to the negative x. 81 is the same as 3 to the 4th power. And if you notice, our bases are the same. When the bases are the same, the exponents have to be equal. So now I write an equation out of my exponents. Essentially, the 3's, the bases, disappear. So x equals negative 4. Here's another example. 2 to the x plus 4 equals 8 to the x minus 6. I have variables in the exponent spot, so these are definitely exponential equations. So I'm trying to decide, can I rewrite 2 and 8 using the same base? Again, consider the two numbers 2 and 8. Think about the smaller value, 2. Can I rewrite 2 and 8 as 2 to a power? Well, obviously, 2 to the x plus 4 is already using 2 as a base. 8 is the same as 2 to the 3rd power. Now, the properties of exponents tell me I need to take 3 and multiply it by x minus 6. That's where we get 3x minus 18. So all we've done is change what we started with, 2 to the x plus 4 equals 8 to the x minus 6, into 2 to the x plus 4 equals 2 to the 3x minus 18. So property B on our list of properties says, if the bases are the same, the exponents have to be equal. Again, notice the bases have disappeared. We don't care about them anymore. Solving for x, we get x equals 11. The last example, b to the 4/3 equals 81. This last example is a little different because the variable b is not in the exponent spot. So this is not really an exponential equation. We already know how to solve this. We're going to change the 4/3 exponent into the cubed root of b to the 4th power, and then go from there. We're going to take the 4th root of both sides to get rid of the 4th power. Now, because the 4th root is an even root, there are two values for the 4th root of 81, both positive 3 and negative 3. Now I've got the cubed root of b equals plus and minus 3. We want to cube both sides to get rid of the cube root. So I have two answers because the cubed root of positive 3 is 27 and the cubed root of negative 3 is negative 27.